Welcome back, everyone. This is Worksheet 3.1, Total Differential Chain Rule and Mixed Derivatives Applied to Thermodynamic Variables. Okay, let's start by imagining a function of three variables this time. Maybe this represents, I don't know, the magnetic field at some position x, y, z in space, or maybe it represents a density of a fluid at some position in space. It can represent whatever it needs to. But then imagine that x, y, and z depend on an additional variable t. So maybe x, y, and z are the position of a particle, and the particle is moving according to some function of time. And I don't know, well, whatever it represents, we then would want to write that x is a function of t, and y is going to be a function of t, and z is a function of t as well. Okay, let's write down our total differential for f. We saw that the total differential is partial f partial x dx, keeping y and z constant, plus partial f partial y dy, keeping x and z constant, plus partial f partial z dz, keeping x and y constant. Now, if we think about x, y, and z being functions of t, then you could imagine that we could get derivatives of each of them. And if there is a small change in x, then we could represent that by saying that it is however much x changes with time times some tiny change in time. And we're getting back here to slope equaling rise over run. So if I multiply the run times the slope, then I get the rise. And the same is true for y. A derivative of y with respect to t times some minuscule change in t. And the same is also true for z. A derivative of z with respect to time multiplied times some small change in time. Okay, now let's plug each of these dx, dy, and dz into the total differential above, and let's get a new total differential that has all of these in it. I'm going to have partial f partial x with y and z constant, and this will be multiplied times dx dt, and then this is going to be plus partial f partial y holding x and z constant dy dt, plus partial f partial z holding x and y constant dz dt. And you might be asking, well, what happened to all my dt's? I could have written all of the dt's out beyond here, but I'm going to gather them all together and just multiply the whole thing by dt. All right? So therefore, a small change in whatever this is, the magnetic field or the density or whatever, is equal to indirectly related to the time through the positions. And the positions are directly related to the time, so therefore any tiny little change in t or time or whatever it represents results in some small change in that function f. So we could say that this whole expression inside these square brackets is equal to the derivative of f with respect to time. Okay, flipping the page over, now let's talk about mixed derivatives. Imagine that we have two partial derivatives where we've got, say, a function u, and it's a function of both temperature and volume. Let's just say that that's the case for now. Who knows what it looks like, but we could start by writing down its derivatives at least. we've got the derivative of u with respect to t at constant volume, and we've also got the derivative of u with respect to v at constant temperature. Now, let's take the second derivative of each of these single derivatives and see what happens. So I'll put the derivative of u with respect to temperature in here at constant volume, but then I'm going to get the derivative of this with respect to volume at constant temperature. So I've sort of got some sort of funny double derivative there, but with two different variables instead of both the same variable. And then over here, let's put the partial of u with respect to v at constant temperature. And then we'll get the derivative of that with respect to temperature at constant v. So it's a little bit funny to think about these things, but I think with more practice you'll get more comfortable. And what these are called are mixed derivatives. It's a derivative to mixed derivatives. So it's the derivative in one direction first and then a derivative in the other direction. Now, are these two equal? Try to pause the video and see if you can imagine what you know about derivatives and see if you can decide. Go ahead and pause now. Okay, unpausing. If you marked yes, then that's the correct answer. Indeed, these two things are equal to each other. So that's pretty interesting. And you might ask why, and the answer is because the order of these derivatives don't matter. And if you've had some experience with taking multiple derivatives in calculus, then you'll know this, that the order of the derivatives don't matter. Okay, so here's a funny problem, just to get a little bit of practice. The problem asks, you have a cylinder of radius r and a height h, and its volume is v equals pi r squared h. If you double the radius, how should you change the height to keep volume constant? You may be able to think of a way to solve this problem algebraically, but let's try to solve this problem using the subject of total differentials. Let's start by defining the total differential. dv is going to be equal to the partial of v with respect to r, holding h constant, dr, plus the partial of v with respect to h, holding r constant, dh. And we're saying that there's no change to the volume, so dv will be equal to 0. All right, let's divide both sides of the equation by dr. Obviously, that just becomes 0. And what we'll get is that partial v, partial r, holding h constant, this becomes 1, plus partial v, partial h, holding r constant, and then the derivative of h with respect to r equals 0. And then I can divide, I can move this over to the other side, dv dr h minus dv dr h, and I get partial v, partial h with respect, or keeping r constant, dh dr equals negative dv dr holding h constant. Next, I'm going to divide both sides by dv dh r, dv dh r, and then I can say that the change of the height of the cylinder with respect to r is equal to negative partial of v with respect to r, holding h constant, partial of v with respect to h, holding r constant. Okay, now why don't you go ahead and try to calculate these two derivatives. So pause the movie for a few minutes and go ahead and give those a try. Okay, what are those going to be? V equals pi r squared h. Let's do dv dr constant h first. That's going to be with respect to this r here, so the 2 comes down in front, and then I do -1, and it's going to be 2 pi r h. All right, let's do dv dh, keeping r constant. Then in that case, the h is just to the 1th power, or the 1st power, and that's just going to leave behind pi r squared. If I plug those into my formula here, then I get that h changes with respect to r as 2h, or 2 pi r h divided by pi r squared. Okay, the pi's cancel out, one of the r's cancel out, and that leaves me with 2 negative, okay, I'm forgetting the negative sign, 2h over r. Okay. All right. This is what we're going to use now to get the final formula. I get dh dr equals negative 2h over r. Now what we want to do is to get all the h's on one side and all the r's on the other side. I'm going to multiply both sides times dr, and I'm going to divide both sides times h by h. Then the dr's cancel out, the h's cancel out on that side, and I get that 1 over h dh equals negative 2 over r dr. Okay, next what I need to do is to integrate both sides. I'll have a starting height and an ending height, and I'll have a starting radius and an ending radius. And what this becomes is log h evaluated at h2 and h1, and I'll have the dr, this will equal negative 2 log r evaluated at r1 and r2. Then this will become log h2 minus log h1 equals negative 2 times log r2 minus log r1. But I can use the rules of logland here to my advantage. I know that a subtraction in the real world equals a division in logland, and I can pull this 2 on the inside of the log. Now if I do that, then I get log h2 divided by h1 equals equals log r. I'm going to pull it's actually the negative 2 goes inside, so it's going to be log r2 to the negative 2, r1 to the negative 2. But remember, negative just means to flip it over to get the reciprocal, so this actually is log r1 over squared over r2 squared. Okay, next I'm going to raise e to both sides of this equation, and I'm just left with h2 divided by h1 equals r1 over r2 squared. And what this means is that if I increase the radius by a factor of 2, then r2 equals 2 times r1. then if we plug that into this equation, H2 divided by H1 is going to be R1 over 2R1 squared. And so this is just going, these R's are going to cancel out. This becomes 1/2 squared, which is just 1/4. So H2 is going to be equal to 1/4 of H1. If I double the radius of the cylinder, I'm going to have to quarter the height in order to have the same volume.